All right, so let's move on to section 7.6, which is titled as the lossy line. So in this section, we will discuss more realistic issues about the transmission line. In our previous discussion, our previous derivation, we all assumed that the transmission line is a lossless line, a perfect transmission line. So the signal can propagate on the transmission line, can go back and forth on the line without attenuation. Well, this is not the actual case, not the real case in the real world. Okay, in real world, you will experience some attenuation. The attenuation means loss in the energy. Okay, so the longer or the larger the signal propagates on the transmission line, the smaller the energy it carries with the signal. So that's a sure thing, unless you can reach out to the planet Pandora, which shall show in the next week, right? The movie. 是吗？下礼拜就上了吗？OK， 好 ，Yeah， 所以考完试就可以看了嘛，OK，all right，so and we have already described the distributed equivalent circuit for a lossless transmission line, which is made of series inductor and shunt capacitor. So if a transmission line is真的是粉笔终结者，我不知道为什么会这样。不，你们看一下，你们多幸福啊！你们今年可以在考完试后无忧无虑的过耶诞节，对不对？26号考哦，然后你要担心说我的电磁波期末考的分数还没出来，要求哦。OK， 好啦，所以串联电感跟并联电容哦，串联电感并联电容，这是5号损传输线的 distributed circuit。我每一年都会问那个来考研究所的那个学生说，这个电路可不可以被简化？不行，OK， 我记起来了要是可以简化的话，我干嘛教这么复杂的，对不对？可以被简化的话，就教一个电感，一个电容，一个电阻就好了，对不对？就是不能被简化嘛？为什么？因为你只是一只小蚂蚁啊，对不对？你只看得到前面的，后面的看不到所以不然我们干嘛那么他给保爱为跟他麻烦的，对不？然后 so if we need to consider the loss on the transmission line, you shall add a resistor in series and another resistor in shunt, which you refer as a conductor, G. So it's this more realistic model is referred as the RLGC model, okay, for distributed circuit for transmission line with loss. So I guess I already described what is the mechanism for R, for the series R. What contributes to the resistance that is connected in series with the transmission line. 它的原因是什么？这两个为什么要分开画？因为它们机制不一样嘛。它们的机制不一样，它们画起来都是电阻，所以它们都一样会造成传输线上面讯号的耗损。但是因为它们机制不一样，所以我们不能把它画在一起。那串联的电阻代表了什么？导体贡献的欧米 loss， 它上面的，因为导电系数不是无限大，只要导电系数是无限大，是超导体的话，那这个 R 就可以拿掉了。那下面那个 G 嘞，并联的 G 是什么？它的成因在哪里？传输线跟线中间的那个介质的，那个介质没有完全绝缘。好，理想的话，他们应该要完全绝缘，导电线是零。只要导电线是零的话，这一个 G 所代表的 G 值就等于零，那就是 open circuit 就可以拿掉了。但一般来讲，你传输线里头，你的塑胶绝缘材质再好，都不是它的导电系数都不是绝对的零。一般好的天然材料里头比较好的，像云母的话，好像到10⁻18次方吧。不要还是一个可以看得出来的数字嘛，对不对？所以因为真实材料里头的 ohmic loss 跟 non-perfect conduct，那个不是完美的绝缘的这个特性，所以我这边其实有写了嘛。导体的电阻跟介链材料的导电性造成讯号的耗损。假如没有它们的话，串联电感就是以磁场的方式储存能量，并联电容呢以电场的方式储存能量，它们并不会消耗能量。So a lossy line is characterized by imperfect but good conductors and imperfect dielectric, giving rise to power dissipation along on the transmission line. And well, okay, so here is the illustration for the ILGC model, so that you can see the series resistor is contributed by the resistance of the conductor, or the non-perfect conductivity of general metal conducting material. And the shunt resistor, which it refers as the conductance here, is the conductivity of the dielectric filling, of the or the conductivity of the insulator, because the conductivity is non-zero. So more or less you will dissipate a little bit energy over here. So to the left is an example of the microstrip transmission line. So the ohmic loss is the resistance on these conductors and the this G stands for conductivity of the substrate, dielectric substrate. And in addition, the magnetic field inside the conductor is taken into account by an additional inductance in the series branch. And the distributed equivalent circuit for the lossy transmission line is shown in this figure, where L includes additional inductance just mentioned. Well, that means you have additional factor contributes to inductance and capacitance on the transmission line model. Note that all these labels R, L, G, C are written in calligraphic letters， 花体字那个西方的书法叫做 calligraphic 吧，书法就是 所以以前太无聊了，没有 Netflix 还是什么可以追哈，所以没事只好拿着笔在那边把字写得很花很漂亮这样子哈，好，叫修身养性吧哈 ，OK。所以那个花体字的 RLGC 指的是单位长度的电感、电容、电导、电阻，电导、电阻 ，OK。好，所以你会看到它这个模型里头，它是写 R 乘上 delta Z， 因为 R 花体字的 R 本身跟花体字的 L 本身是单位长度的电阻跟单位长度的电感嘛，你要再乘上它的长度 delta Z， 才会变成是电感值跟电阻值。我是不是 miss 掉下课啊？哦。好，把这段讲完，我们再下课一下，再休息一下好了。好，所以因为物理机制不同嘛，所以这边就分开来放了哈。Alright, so let's take a break of 5 minutes. Alright. So here, due to the presence of lossy mechanism, that is the ohmic loss in the conductor and the imperfect insulation of the dielectric, we introduce the series resistor and the shunt conductor in the RLGC model. Therefore, the transmission line equation should be modified to account for the low C component. So equation 7.62 A and B are transmission line equation from the perspective of voltage and current. So from the perspective of voltage, the voltage difference between the right-hand side and the left-hand side will be the voltage accumulated on the inductor and the voltage accumulated on the resistor. So if you taken the if you subtracting the voltage of V at the position Z plus delta Z, and by V at the left-hand side, that is V at the position Z, it will equals to the minus of R times delta Z, that is the resistance of this section, times the currents on it, because this is a simple resistor. So the voltage difference will be the product of the resistance and the currents. On the other hand, for the inductor, you shall abide the relationship of the voltage and current in terms of inductance. That is, the voltage difference accumulated on the inductor is the product of the inductance, that is L times delta Z, times the time derivative of the current. So here is del I over del T. And the same thing can be performed on the currents. So for the currents, we are kind of writing up the node equation at this position. At this position, you have you have 4 currents. One current to the right, that is I of Z plus delta Z. One current flows from the left into the right is the current of I at the position Z. The difference of the 2 currents will be the sum of the currents flowing down. One is passing through the conductor and the other is passing through the shunt capacitor. So the conductor, it can be written as minus of G times delta Z times the voltage difference across the conductor, and for the capacitor, the currents flowing through the capacitor will be the product of C times delta Z times the time derivative of V with respect to del V over del T. Okay, so you simply add the two modification terms R and G into the original transmission line equations. So if you take in the limits, that is delta Z approaches to 0, then the transmission line equation can be simplified as the two shown in 7.63. Okay, now, so the two terms in the red dashed line are the Ohm's laws and the conductance on the dielectric. Then these two equations can be further simplified in terms of phasor expression. So you can drop the dependence with respect to T, and by acknowledging that the signals are all sinusoidal signals of a specific frequency, then the voltage and currents can be written as in this form, okay? And if you collect the current terms and voltage term and replace the time derivative with j omega, then it can be further simplified as equation 7.64. So low looks like the for both V and I, they are all functions of Z, of position Z. Then we can further develop our transmission line equations by what we have done before. We taking another derivative on both sides. For example, if we take spatial derivative on equation 7.64a again, then the derivative of V with respect to Z becomes to the square of a second derivative of V with respect of Z. And on the right hand side, you are taking the derivative of I with respect to Z. And note that this spatial derivative of current can be replaced with equation 7.64b. So with this substitution, the equation, the second order derivative of V equals to R plus j omega L times G plus j omega C times V. So it becomes in the form of a wave equation. It's a second order partial differential equation. To the left are spatial derivative, second order spatial derivative. To the right is second order time derivative, which is not explicitly shown because it's collected as gamma to the square. But if you look carefully, the gamma to the square is actually the product of R plus j omega L times G plus j omega C. J omega L and j omega C all stands for time derivative. Time derivative. So the right hand side of the equal mark of 7.65 is actually a second order time derivative. Second order time derivative. But anyhow, equation 7.65 is in the form of wave equation. So gamma is referred as the wave propagation constant. And it's a combination of alpha plus j beta. Beta is what we refer as the phase constant when we're dealing with lossless transmission line. So if you check up the equations in chapter 5. This thing is应该是加的嘛，对，加贝塔平方。7.56拿过来的话是减伽马平方嘛，减伽马平方 b。但假如你是贝塔的话，因为它事实上是 j 贝塔的平方 ，j 贝塔平方就变成负的贝塔平方嘛，所以拿过来左边之后变成加的，但假如是 lossy 的话，就是所以差别在这边So for the propagation gamma is referred as the propagation constant. It's a combination of attenuation constant alpha and the phase constant beta. And it's so propagation constant gamma is a complex number. The real part is referred as the attenuation constant, which stands for the loss in the transmission line. And beta is the phase constant, which stands for the phase variation of the signal propagating in the transmission line. So ideally, we hope to minimize the alpha value. The smaller the alpha, the less loss we take from this transmission line 所以 alpha 值要尽量的减少，我们希望 alpha 值越小越好 ，OK， 好，那贝塔的话，因为它是 J 贝塔嘛，所以它是一个 complex number， 所以你把它放到那个 exponential 里头 ，exponential minus J 贝塔 z， 这个东西的特色是什么？不管贝塔 z 是多少，它的 magnitude 都等于1。好，所以假如你是无耗损的传输线的话，你的 z 不管怎么变，它的那个讯号的大小都还是1，都还是原来的大小，没有 attenuation。但是同样的式子，假如 alpha 是不等于0的话，它就会变成的负 alpha z 在前面。所以 z 假如越来越大，然后 alpha 值不等于0的话，你的讯号就会越来越小。对不起，有一件事我刚才没提到，在伽马里头 ，alpha 跟贝塔都大于0，大于等于0了。贝塔是大于0了，不然你就不是电磁波了哈。那 alpha 是大于等于0，所以它们 alpha 跟贝塔都是正实数。Positive real number. So even though that gamma is a complex number, it's actually located in the first quadrant of the complex plane because both alpha and beta are positive real number. Okay? And the relationship between the propagation constant gamma and the other transmission line parameters is this. Gamma equals to the square root of R plus J omega L times G plus J omega C. Okay? So once you find out the model parameters, I mean R, L, G, C, you can derive the corresponding attenuation constant alpha and the corresponding phase constant beta. Okay. So what is the lossless case? if you have a lossless transmission line, alpha equal to 0, R equal to 0, G equal to 0, then gamma equals to to J beta, gamma equal to J beta, and J beta equals to square root of omega to the square times LC 哈，所以自己比一下吧哈。假如没有耗损的话，什么叫没有耗损 ？R 等于0 ，G 等于0 ，A 等于 alpha 等于0啊。那剩下来的东西就是 J omega L 乘上 J omega C， 就是 J beta 的平方。Okay. All right. So here is the general expression for the voltage signal on the transmission line. By substituting the phase constant with propagation constant gamma, then on the transmission, we know that on the transmission line you can divide the signal into forward going wave and the reverse going wave, So as the picture shown, A times exponential minus gamma z stands for the forward going wave, that is traveling to the positive z direction. And on the other hand, the second term, B times exponential gamma z, stands for the reverse going term, which travels towards the minus z direction. If you substitute other parameters into the expression of the voltage, that is the instantaneous form of the line voltage. 我刚刚讲 instantaneous form 指的什么意思 ？T 有跑出来了，上面那个是 phasor form， 上面那个没 T， 对不对？所以上面那个我指的是 phasor form。好，那 T 的 dependence 就你知我知，我们不写出来。但下面这个是 instantaneous form， 我就明明白白的写出来。那它跟 phasor form 的关系是，你把 phasor form 乘上 exponential j omega t， 然后再取10步，啊，所以那个中间那个式子的那个中括弧哈，其实就是原来的那个 vz 的式子乘上 exponential j omega t， 外面再取10步。所以取10步完之后 ，exponential j omega t 就变成是 cosine function， 啊，所以上面的话你看到有好几个项，这个是常数 A 本来的相角，这个是讯号在传输线上面走不同的 z 的位置所看到的相角，后面这个是 time dependence 不同的时间所引出来的相位变化。所以后面这跟着4个 exponential， 你有没有看到？有3个都是虚数的，3个都是虚数的指数啊。所以这3个虚数的指数，它的 magnitude 都不会变，都是1，但它相角会变化。所以你要写出它的10步的时候，你就把它们的相角的表示是集合在一起，所以你这边会变成 cosine 的 omega t 减 beta z 加 theta， 后边那个嘛赶快变成是 omega t 加 beta z 加 phi， 加 phi， 但这4个 exponential 有一个不能够被跟人家合在一起，也就是它有实数的指数啊 ，exponential minus alpha z and exponential alpha z 啊 ，because because they are of real numbers, so they cannot merge with imaginary exponential of imaginary index. So it's exponential minus alpha z. So the magnitude of this thing change as z value varies. 所以 alpha 只要是不等于0，那么 z 值变化的话 ，exponential minus alpha z 的大小 magnitude 也会变化。注意，这个 alpha 它是一个 real number， 它是一个 real number， 而这一个部分呢，代表的是往正 z 方向传的，所以它的 z 值会越来越大。 z 值会越来越大，然后阿尔法又是一个正数，所以这个指数的部分它会越来越负，越负越多，然后嘞，讯号就越来越小，然后最后会死翘翘，会变不见。好，那后面那个的话也要满足这个物理的直觉嘛，对不对？它写起来是 exponential alpha z， 跟前面这一项差一个负号，但是后面那个它代表的是往负 z 方向走的讯号，所以它越往负 z 的方向传，它的 exponential 的值的那个指数的部分也是越来越负，所以它一样讯号越来越弱。啊，所以在没有外力介入的状况底下的时候，你就没有额外插电的话，你的讯号都是会越来越小。因为讯号都会被动元件来讲，讯号都马是越来越小。So we see that the first and second terms on the right-hand side corresponding to wave propagating in the positive z direction and the negative z direction respectively. So we can rewrite equation 7.67 as this, which is further simplified as two components with a v plus component and v minus component. V plus component is propagating toward the positive z direction, while the v minus component is propagating toward the negative z direction. And the quantity beta, which I already said that it's the imaginary part of the propagation constant gamma, is referred as the phase constant. So it represents the phase change with respect to the position z at a fixed time. Okay, so what is the other expression for beta? Yeah, for myself, I always remember that beta equals to 2 pi over lambda, which can be changed into 其实另外一个我一直背不起来，是 W over F 还是 F over W？W 等于什么 ？2 pi F。哦 ，OK，W over C。哦 ，OK，C 的话就等于 lambda F 嘛，上面是2 pi F。OK， 好，好，所以 W over C。W over C 啦，或有的时候是写作 W over V，OK， 也可以。好，很好，尽量记下来了哈，这样记下来比较方便一点。所以意思是什么？只要你的贝塔值越大，就表示你的lambda值越小。波长越短，频率越高，所以高频率的讯号，它的贝塔值会变高。意思是说，它走同样的距离的话，高频的讯号它所经历到的 experience 的 phase change 会比较多，低频的讯号就慢慢的360度，高频讯号就因为它波长短嘛，所以那个360度变化会比较剧烈。The quantity alpha, which is the real power of the propagation constant gamma, is referred as the attenuation constant, which denotes that the wave gets attenuated by factor exponential alpha per unit distance as it propagates in their respective directions. And the unit for alpha can be nepers per meter or nepers per wavelength。所以 alpha 的单位不一定啦，有的时候是每波长的那个的 attenuation， 或者是每实际的距离的那个 attenuation。所以假如你写作 neper per meter 的话，就是实际距离的那个讯号衰减。但有的时候写作那个 neighbor per wavelength 也不一定啊。So proceeding further, we obtain the corresponding solution for the phasor line currents by substituting equation 7.60a into one of the transmission line equation. So originally we have this equation 7.60a, and if you taking the derivative of v with respect to z using equation 7.68, you end up with minus gamma v exponential minus gamma z plus gamma times v exponential gamma z, okay? And with some substitution using the express definition of gamma, that is this one. Gamma equals to the product, the square root of the product of this times this. So if you 你有看到这边的话，我们甩出两个伽马出来，所以把这两个伽马用右下角的那个阿尔法加 J 贝塔等于开根号的那个巴拉巴拉巴拉取代掉之后，跟这个所在跟下面的 R 加上 J 欧米伽 L 倒起来，好，你就会看到它会变成是一个 ratio。事实上，这个地方插进去之后，会变成是 G 加上 J 欧米伽 C 除上 R 加上 J 欧米伽 L 开根号。但因为这边是电流跟电压嘛，那 Z 又是电压 over， 我的中英文都夹在一起了 ，voltage over current Because the definition of the impedance is voltage over current, so you take in the inverse of the product over here. It turns out to be in the form of the impedance, which is the ratio of the voltage over current is this. So you have R plus J omega L divided by G plus J omega C, and taking the square root of this will be the characteristic impedance of the line. So things are getting very complicated, right? The expression becomes much more complicated. What is the significance of the presence of R and G? The presence of R, if there is no R and G, if there is no loss, if there is no resistance in the conductor, if there is no conducting currents in the dielectric, then R goes to 0, G goes to 0, then the characteristic impedance will be the ratio of J omega L divided by J omega C. The J omega part can be cancelled. So it's simply the square root of L over C. So that's what we have for lossless transmission line. Now we have a lossy transmission line. So what is the immediate consequence of this thing of the R and G? Damn. The characteristic impedance is a complex number, right? It becomes a complex number. What is the significance of a complex number Z? Means the voltage and the currents are not synchronized. If the transmission line is lossless, the characteristic impedance is a real number, which means there is no phase difference between the voltage signal and the current signal. Now Z becomes a complex number. It has a phase term. It has a phase difference term. So that will be the phase difference between voltage signal and the current signal. Fortunately, most of the transmission line we are using are low loss transmission line. If it's a really transmission line, you should throw it in the trash can, right? Why use a very lossy transmission line? It's of no use. Signal gets attenuated inside the line, right? So, fortunately, most of the transmission lines that we are using are low loss transmission line, which means R and G value are relatively small comparing to J omega L and comparing to the J omega C. So if this is the case, even though that the Z, the characteristic impedance, is a complex number, but it's a complex number with a very small angle. So the voltage and the currents are largely in phase. So we can neglect the presence of I and G when it turns to the characteristic impedance. We just take it. It's about 50 ohm. Yeah. So if you considering the loss in your transmission line, it's not 15 ohm. It's 15 ohm with some imaginary part. Yeah, but that's a small number. So most of the time you can just neglect it. Yeah. Okay. So for lossy transmission line, the characteristic impedance is not necessarily a real number. It can be a complex number, which represents the loss, the impact of the loss. And all right, so that's the low loss discussion about low loss line. I guess we stop here. Okay, we will continue tomorrow for the. No, not tomorrow. Next week. 好，我们今天到这边了。OK，剩下我们下礼拜再讲。